Assalamu alaikum. All of my dear students, you are most welcome in my physics class today. We know from our Newtonian mechanics, a mass is a constant scalar quantity. It doesn't depend or change with time or any motion of any object. But in theory of relativity, Einstein expressed mass does not constant of any object. It's a relative quantity. That means mass has a relation with the motion of its. When the object is in motion, the counting mass is larger or more than it is when it is rest. And this phenomenon I want to describe to you in my today's class. So let us start. To understand the effect of relativistic mass, you have to learn few equations. First of all, m equal to m naught by root over 1 minus v by c whole square. This is a very well known and basic equation, and by using this equation you also learn and know the effects of the relativistic mass on the other sector, like total energy of the object, kinetic energy of the object when it is moves in near about the light velocity, and also the momentum of the object and change of the momentum of the object. And here you also observe that Kn means it is a very well known half mv square equation. This is the equations of kinetic energy as per the Newtonian mechanics, and here also P equal to mv, and here Pn, which suggests that the moment of Newtonian mechanics. Here m equal to relativistic mass, and m naught, which is the rest mass, when the observer and object is in same velocity, which is called with the rest position, and the counting mass is called the rest mass. When object and observer is in a different velocity, which is called the moving position in respect of the observer. And in this case, the measurement of the mass is called the relativistic mass, and another meaning is the mass in motion. Velocity of the object is a relative velocity in between object and observer. See the light velocity, here you observe the c, here also c, here also c. This c is the light velocity, 3 into 10 to the power 8 meter per second. E total energy, k for kinetic energy, and m for momentum energy. Let's students, now we start the practice of this relativistic mass and also understand the effect of this mass in the other sector. So let's start. Students, here is our first CQ for today's. The velocity of two electrons of an electron is 0.9 c. That means is almost 90% velocity of the light, and 0.99 c respectively. Here c is the velocity of the light, and the rest mass of an electron, which is given 9 into 10 to the power minus 31 kg. The first mass math for the stem. Determine the moving mass of the second electron. Second electron, that means which the electron is moving with the 0.99 c velocity. The first one is moving with the 0.90 c velocity. Now the given one, answer for the C. Determine the moving mass. We know the equation of the moving mass is m equal to m naught divided by root over 1 minus v by c a whole square. Here the moving mass on rest mass m naught equal to, which is given 9 into 10 to the power 9 into 10 to the power minus 31 kg, and the moving mass is required, and the velocity of the electron is the velocity of the second electron is v equal to 0.99 c. Now put the value on the equation here. 9 into 10 to the power minus 31. We can cut the value of the c here. We also put the value of the c and cut these two datas. 0.99 square, and by using the calculator we can find the result 6.451 into 10 to the power minus 6.451 into 10 to the minus 30 kg, which is slightly greater than from the rest mass. When an object moves with near about the light velocity, the mass will increase, and this phenomenon is called the increase of mass, and which is called the relativistic mass. And this is for the C. Now for the next one, the relative kinetic energy of which electron is more, as in the stem. Here two electron, first one moves with 0.9 c velocity and second one moves with the 0.99 c velocity. We already know about the moving mass of the second electron, but we here the missing data is for the moving mass of the first electron. Now need to find the first time the data of the moving mass of the first electron. So boys, the answer for the D, m equal to m naught root over 1 minus v by c whole square. The velocity of the first electron, velocity 0.9 c. So 9.1 into 10 to the power minus 31 as per the question number C, 0.9 c. After omit these two data is light velocity c, we can find the result 2.087 into 10 to the power minus 30 kg. Now the relativistic kinetic energy. Kinetic energy as per the theory of relativity, m minus m naught c square. For the first electron, k1 and m1, and for the second electron we can easily choose k2 m2 minus m naught c square m1 we can omit the rate of c, m2, the moving mass of the second object, second electron, 2.087 10 to the power minus 30, 9.1 into 10 to the power minus 31, m1, the moving mass of the first electron, which is already we determined in the our c. After using the calculator, we can write here k1 by k2 equals to 4.7, so that we can make a comments here. The kinetic energy of the second object, second electron, is 4.7 times of the kinetic energy of the, so the relativistic kinetic energy of the second electron will be the more. Students, here the second question. In the physics library, Mr. Hassan found the density of a 1 meter long metallic object 19.3 10 to the power 3 kg per meter cube. On the other hand, Pabuni determined the density of the object in the moving frame moving with 0.9 c along the length of the object. The rest mass of the object is 2000 kg. Find the total energy of the object in the moving frame. We know the total energy of the object. Here the answer for the C, we know the total energy equation equal to mc square. Here the question is for the moving frame, so we know another equation for the mass in constant for the moving frame. Here m naught by root over 1 minus v divided by c whole square, here also c square. M naught is the rest mass. The given the rest mass of the object is 2000 kg, so that the rest mass v is for the velocity. Velocity also given 0.9 c. C is the light velocity. 3 into 10 to the power 8 meter per second. Now put the value on the equations. 2000, 0.9 c by c whole square, here also another c square, 2000, 0.9 square, 3 into 10 to the power 8 whole square. After calculating this data, we will find that 4.12 into 10 to the power 20, the total energy. So that is Joule is the answer for C. Now the question number D. Will Mr. Hassan and the Pavani get the density of the object same? We observe that in the stem here, the measurement in the lab, the density is 19.3 into 10 to the power 3 kg per meter cube. But the Pavani determined the density of the object when the frame is in moving with the velocity 0.9 c. And now we determine the density in the moving frame. So we can consider that. Now the answer for the D, in the lab, area of cross section equal to A naught, and the volume of the object also V naught. In moving frame, area of cross section equal to A, and volume equal to V. We know M equal to m naught root over 1 minus V by C whole square. After dissolving the mass, we can find the volume and density also. M equal to V rho is in moving frame, m naught V naught rho naught root over 1 minus V by C whole square. Inside the V, AL, area of cross section, and the length of the object rho, A naught, L naught, rho naught 1 minus V by C whole square. Here we observe that A equal to A naught. Why A equal to A naught? The area of cross section in the lab, that's been rest reference frame, and area of cross section is in moving reference frame. Both are equal because the object moves along the length of the length. When the object moves along the length, or according to the direction of the length contraction only be taken place, so that the area, this constant area, is there is no change in observed across the area of cross section, so that we can deduct this A and A naught. Now here present is L. We know another equation for this L naught root over 1 minus V by C whole square, L naught rho naught root over 1 minus V by C whole square. So we can easily find here, also deduct L naught and L naught, here rho is present, so that rho equal to rho naught. After multiplication these two items, we can write here 1 minus V by C whole square. Here the density of the object in rest reference frame, the given is 19.3. in rest, rho naught 19.3 into 10 to the power 3 kg per meter cube. 19.3 10 to the power 3 1 minus V by C 0.9 cc. After calculating the data, 0.1 into 57 kg per meter cube. So that the density does not equal to the density which is measured by the Hassan. Now the question number, that's mean stem number 3. Here we observe that a particle rest mass is 9.1 10 to the power minus 28 kg. It moves with a speed of 0.9 c. Speed of light also be given here. It is a very short stem, but the maths are very important because we observe that here determine the momentum of the particle when it is moving. Momentum. We know the momentum. How can you find the momentum? The product of mass and velocity, which is known as the momentum. That's when we can answer this question number C. We know momentum P equal to mv. M is the mass, and which type of mass is now this is the question now. Is the moving. When it is moving, momentum need to find in moving condition, the moving observer. That's mean this mass is in moving mass, and we know the equation of the moving mass is m naught root over 1 minus v by c whole square. This is a v. M naught, the rest mass. The rest mass also given 9.1 10 to the power minus 21 here. And the speed of the object also v equal to 0.99 c. So put the value and find out the required result. 9.1 into 10 to the power minus 28, 1 minus 0.99 c and c into 0.99. Velocities, the data of the c is 3 into 10 to the power 8. After calculating the data, the result is 1.91 into 10 to the power minus 18. The momentum kg meter per second. This is the answer for C. Now the question number D. Analyze in the light of the data given in the stem that kinetic energy obtained from Newtonian mechanics is not same as the obtained kinetic energy in theory of in concern for the theory of relativity. So we know the question number D, the kinetic energy in Newtonian mechanics K naught equal to half m naught v square, and the kinetic energy in theory of relativity K r equal to m minus m naught c square. The second. Why here m naught? Because in concern for the Newtonian mechanics and in the time of Newtonian, we already learned in our first paper also, there is no stage at the change of mass. That's when mass is absolute. There is no change in Newtonian mechanics of the mass in respect of the moving. In theory of relativity only we learn about this phenomenon. When object is moved near about the light velocity, the mass is increasing. And this change of mass only observed in the theory of relativity, but in the Newtonian mechanics, mass always the rest quantity, which is already given in this step. But m is need to find here. So after using the first number equation from 1 kn half m naught v square. The speed of the light 0.9 c. So the value is for calculation 4.01 into 10 to the power minus 11 joule. This is the equation for the kinetic energy in Newtonian mechanics. Now we can find from the second equation Kr m minus m naught c square. Here m is the moving mass, so we need to find the moving mass also. M naught root over 1 minus v by c whole square. Here m naught c square. We can make also common here m naught 1 minus, put the value v also, 0.99 c divided by c whole square minus 1 m naught c square. After calculating the data, 6.08 m naught c square, 6.08 m naught. The rest mass 9.110 to the power minus 20, and finally Kr equal to 4.97 into 10 to the power minus 10 joule, which is not equal to the kinetic energy which is observed in our Newtonian mechanics, in form of Newtonian mechanics. So that this is not same. No, it's not same. The speed of atomic particles like electrons, protons and masons, so on, they are moves with high velocity, and this relativistic mass is highly observed and measurable in those particles, characters. So if you want to learn more, you stay tuned with physics, stay tuned with me. Thank you today. Goodbye. Allah Hafiz.